Welcome! Today, we'll be tackling LeetCode problem number 1971, find if path exists in graph. This problem is a fun and practical exploration of graph traversal techniques. You'll get to strengthen your understanding of undirected graphs while applying algorithms like DFS or BFS to determine if two nodes are connected. Let's dive in. In this problem, we are tasked with determining whether a valid path exists between two nodes in an undirected graph. The graph consists of n nodes, labeled from 0 to n1, and it is represented using a 2D array called edges. Each pair in edges defines an undirected connection between two nodes. Additionally, we are provided two specific nodes, source and destination, and our goal is to check if we can traverse from the source node to the destination node, following the edges of the graph. The output will be a Boolean value, true if such a path exists, and false otherwise. The inputs include the number of nodes n, the list of edges, the source node, and the destination node, while the output is a simple true or false indicating the existence of the path. Let's look at an example to clarify the problem. Suppose the graph consists of three nodes with edges defined as 0, 1, 1, 2, 2, 0. The source node is 0, and the destination node is 2. The graph structure allows us to visualize that node 0 is connected to node 1 is connected to node 2, and node 2 is connected back to node 0. This means that there are multiple paths from node 0 to node 2, such as 0, 1, 2 or directly 0, 2. Because at least one valid path exists, the output for this input is true. Now, consider another example where the graph has 6 nodes and edges as 0, 1, 0, 2, 3, 5, 5, 4, 4, 3. The source node is 0, and the destination node is 5. Here, the graph can be divided into two disconnected components, one consisting of nodes 0, 1, and 2, and the other consisting of nodes 3, 4, and 5. Since there are no edges connecting these two components, it is impossible to traverse from node 0 to node 5. As a result, the output in this case is false because no valid path exists between the source and destination nodes. In a simpler example, the graph contains only one node, n equals 1, with no edges. The source and destination nodes are both 0. Since there is only one node and it is both the starting and ending point, a valid path trivially exists. Thus, the output is true. This demonstrates that even in cases where there are no edges, a path exists if the source and destination are the same node. To summarize the problem, there are key constraints and edge cases to consider. The graph can have up to 200 nodes and edges, and there will be no duplicate edges or self-loops. If the graph consists of only one node, a path exists only if the source equals the destination. If there are no edges in the graph, the path also requires the source and destination to be the same. Furthermore, if the source and destination belong to different connected components, no path can exist. However, if the two nodes are directly connected by an edge, a path always exists. These edge cases help us better understand how to approach the problem in all scenarios. To solve LeetCode problem number 1971, we are tasked with determining if there is a path between two nodes in an undirected graph. One of the approaches we can consider is using an adjacency matrix combined with depth-first search, or DFS. The intuition here is straightforward. The adjacency matrix explicitly represents all edges in the graph, and DFS explores one path fully before moving on to another. This approach works particularly well for small graphs because adjacency matrices are simple and direct. However, it comes with some notable limitations. While the time complexity for constructing the matrix and performing DFS is manageable, the space complexity is n squared, which becomes impractical for larger graphs, especially when the graph is sparse. This means that for very large graphs, such as those with 100,000 nodes, an adjacency matrix can be extremely memory-intensive and inefficient. Another approach to consider is using an adjacency list combined with either DFS or breadth-first search, or BFS. The idea here is to represent the graph more efficiently by storing only the edges that exist, making this method especially suitable for sparse graphs. Both DFS and BFS can be used to traverse the graph and check for connectivity between the source and target nodes. BFS is often preferred for tasks like finding the shortest path, while DFS is better for exhaustive exploration. The time complexity for this approach is n plus e, where n is the number of nodes and e is the number of edges, and the space complexity is also n plus e, which is much more efficient than an adjacency matrix for large, sparse graphs. However, even this method has limitations, as the space required still scales with the number of edges. Another option is the union find approach, which identifies connected components in the graph. By using path compression and union by rank, union find allows for almost constant time connectivity checks. While union find is excellent for repeated dynamic queries, it does require pre-processing all edges, which may not be ideal for single query scenarios. For this problem, we chose to use the adjacency list representation combined with BFS or DFS. This decision was based on a few key reasons. First, BFS is particularly well suited for checking connectivity between nodes, as it systematically explores all neighbors before delving deeper. Second, the adjacency list representation is highly efficient in terms of memory usage, especially for sparse graphs, which aligns perfectly with the problem's constraints. With up to 100,000 nodes and 200,000 edges, scalability is crucial, and this approach balances simplicity and efficiency. While union find offers faster dynamic connectivity checks, it requires pre-processing all edges, which is unnecessary for the single query problem. Overall, BFS with an adjacency list allows us to traverse the graph efficiently and answer the connectivity question without introducing unnecessary overhead. However, it's important to note that BFS and DFS both process all nodes and edges in the worst case, which could be slower than union find for repeated queries. The undirected nature of the graph simplifies traversal since edges can be treated bidirectionally, which eliminates the need for additional handling of edge directions. BFS is particularly well matched to this problem because of its level-order nature, ensuring all neighbors of a node are explored before any deeper traversal takes place. This systematic exploration aligns well with the requirements of checking connectivity. The adjacency list representation strikes a balance between memory efficiency and traversal effectiveness, making it ideal for large-scale graphs. Ultimately, the combination of an adjacency list with BFS or DFS was chosen because it provides a practical solution that is simple to implement, efficient in terms of both time and space, and scalable to handle the problem's constraints effectively. This approach allows us to navigate the graph structure with minimal overhead while ensuring clarity and correctness in solving the problem. In this problem, we are tasked with determining whether a path exists between two nodes in an undirected graph. This is a classic example of a graph traversal problem, and we can solve it efficiently using depth-first search, DFS, or breadth-first search, BFS. To approach this problem, we start by parsing the input. We are given n nodes, numbered from 0 to n1, and a list of edges where each edge connects two nodes. Along with this, we are provided two specific nodes, a source node and a destination node. The goal is to check if a path exists between the source and destination. For example, if n equals 5, the edges are 0, 1, 1, 2, 2, 3, 3, 4, and the source is 0 while the destination is 4, the output is true because a path exists from 0 to 4 through nodes 1, 2, and 3. To represent the graph, we use an adjacency list. This data structure is both space-efficient and traversal-friendly. For instance, the adjacency list for the given edges would store connections like so: node 0 connects to 1, node 1 connects to 0 and 2, and so on. This representation ensures that we can efficiently explore the graph during traversal. Once the graph is represented as an adjacency list, the next step is to traverse it using DFS. To avoid revisiting nodes and potentially entering infinite loops in cyclic graphs, we maintain a visited set. This set tracks all the nodes we have already processed. With the visited set in place, we define our recursive DFS function. Starting from the source node, we recursively traverse its neighbors. For each node, we mark it as visited. If we encounter the destination node during this process, we immediately return true. Otherwise, we explore all unvisited neighbors of the current node. If none of the neighbors lead to the destination, the function eventually returns false. The base case for the recursion is simple: if the current node is the destination, we stop the recursion and return true. During the traversal, we also ensure that nodes already in the visited set are skipped to prevent redundant processing. This approach systematically explores all possible paths from the source to the destination while ensuring cycles do not cause infinite recursion. As the DFS function processes each neighbor, it recurs on the neighbor and propagates the result back up the call stack. Once the traversal is complete, we check the final result of the DFS call. If it returns true, there is a path from the source to the destination, otherwise, the output is false. A few key insights can help us understand this approach better. First, since the graph is undirected, each edge, u, v, implies bidirectional connectivity between nodes u and v. This is why, when building the adjacency list, we add both directions for each edge. Second, the use of the visited set is crucial for handling cycles in the graph. By marking nodes as visited, we prevent infinite recursion and ensure that each node is processed only once. Finally, while we focus on DFS here, BFS is another viable option. DFS is more space efficient for deep exploration but may hit recursion limits in large graphs. BFS, on the other hand, uses a queue and guarantees shortest path discovery in unweighted graphs but at the cost of higher space usage. Additionally, we must consider edge cases, such as disconnected graphs where the source and destination are in separate components, or graphs with no edges where we directly check if the source equals the destination. To implement this solution effectively, we rely on two main data structures. First, the adjacency list, which has a space complexity of O, n plus e, where n is the number of nodes and e is the number of edges. This is particularly efficient for sparse graphs as it avoids storing unnecessary information. Second, the visited set, which has a space complexity of O, n, as it tracks whether each node has been processed. Next, let's analyze the time complexity of the algorithm. Building the adjacency list takes O, e, time since we process each edge once. The DFS traversal takes O, n plus e, time because each node and edge is visited exactly once. Combining these, the overall time complexity is O, n plus e. Space complexity also includes the adjacency list, the visited set, and the recursion stack for DFS, all of which together require O, n plus e, space. This makes the algorithm efficient for solving the problem within reasonable constraints. Now, let's explore an example to see the algorithm in action. Consider an input where n equals 5, the edges are 0, 1, 1, 2, 2, 3, 3, 4, the source is 0, and the destination is 4. First, we build the adjacency list. The resulting graph representation is as follows: node 0 connects to 1, node 1 connects to 0 and 2, node 2 connects to 1 and 3, node 3 connects to 2 and 4, and node 4 connects to 3. With this graph structure, we initiate the DFS traversal starting at node 0. We mark node 0 as visited and explore its neighbors. The neighbor 1 is unvisited, so we move to 1 and mark it as visited. From node 1, we explore its neighbors 0 and 2. Node 0 is already visited, so we move to node 2. This process continues recursively, visiting nodes 3 and finally 4. Since node 4 matches the destination, the function returns true, indicating that a path exists. After successfully reaching the destination node, the algorithm outputs true. This example demonstrates how the DFS traversal efficiently finds a path by exploring neighbors recursively while avoiding cycles using the visited set. To optimize further, we could use BFS with a queue for iterative traversal, which avoids recursion stack limits. Additionally, we can skip adjacency list construction entirely if the source equals the destination, as the answer in that case would always be true. Another optimization involves a pre-check for edge count. If there are no edges in the graph, we simply check if the source equals the destination. These optimizations ensure the algorithm remains robust and efficient for a variety of input scenarios, making it a versatile solution to the problem. Here, we begin by importing two essential modules, defaultDict from the collections module to handle the adjacency list and Deek to facilitate the breadth-first search, or BFS, traversal. Inside the valid path function, our first step is to construct the graph using an adjacency list. We use a defaultDict of lists to store the connections between nodes. For each edge in the input list, we add the nodes to each other's adjacency list, ensuring our graph representation captures the bidirectional nature of the edges. Next, we initialize a visited set to keep track of nodes we've already processed and a queue, initialized with the source node, to manage the BFS traversal. The BFS loop begins by dequeuing a node for processing. If this node matches the destination, we immediately return true, as we've confirmed a valid path exists. If not, we mark the node as visited and prepare to explore its neighbors. To explore the neighbors, we iterate over each neighboring node connected to the current node in the graph. For each neighbor, we check if it hasn't been visited yet. If it's unvisited, we add it to the queue, ensuring it will be processed in future iterations. This process continues until the queue is empty. If the BFS completes without finding the destination node, meaning no path exists between the source and destination, we return false. This approach guarantees that we explore all possible paths systematically while avoiding revisiting nodes, thanks to the visited set. By the end of this function, we'll have either confirmed a path exists or ruled out the possibility, achieving the desired result efficiently. In this implementation, we start by importing the necessary Java utility classes for handling collections. The method validPath is defined to determine if there is a path between the source and destination nodes in a given graph. The first step is to build an adjacency list representation of the graph. We initialize a hash map where each node is mapped to a list of its neighbors. For every edge in the input, we add the two connected nodes to each other's adjacency list, which ensures the graph is represented as an undirected structure. Next, to determine if a path exists, we use a breadth-first search approach. We initialize a set to keep track of visited nodes and a queue to manage the nodes to explore, starting with the source node. The while loop begins processing, where we pull the front node from the queue. If this node matches the destination, we immediately return true, indicating that a path has been found. If the current node is not the destination, we mark it as visited by adding it to the visited set. We then iterate over all its neighbors in the adjacency list. For each neighbor, if it hasn't been visited yet, we add it to the queue for further exploration. This ensures that BFS systematically explores the graph layer by layer, checking all potential paths. If the queue is exhausted and the destination has not been reached, we return false, as no valid path exists between the source and destination. This implementation efficiently leverages BFS to ensure we explore all possible connections while avoiding cycles, thanks to the visited set. Let's begin with example 1, where we have a simple connected graph. The input gives us 3 nodes, edges connecting them, and we need to determine if there is a path from node 0 to node 2. First, we construct the graph using an adjacency list representation. This results in a dictionary where each key is a node, and its value is a list of neighboring nodes. For this graph, we get 0 is connected to 1 and 2, 1 is connected to 0 and 2 is connected to 1 and 0. Next, we initialize a breadth-first search, or BFS, by adding the source node, 0, to the queue and creating an empty set to track visited nodes. In the first BFS iteration, we dequeue node 0 and check if it matches the destination node, 2. It doesn't, so we mark 0 as visited and add its unvisited neighbors, 1 and 2, to the queue. In the second iteration, we dequeue node 1, check if it matches the destination, and again it doesn't. We mark 1 as visited and add its unvisited neighbor, which is 2, to the queue again. Finally, in the third iteration, we dequeue node 2, which matches the destination. At this point, we return true, indicating a path exists. Now, let's analyze example 2, where the graph is disconnected. The input specifies 4 nodes and edges that connect only node 0 to 1 and node 2 to 3, with no connection between these two pairs. The task is to find if there's a path from node 0 to node 3. First, we construct the adjacency list. Here, 0 is connected to 1, 1 is connected back to 0, 2 is connected to 3, and 3 is connected back to 2. With the graph ready, we initialize BFS by adding the source node, 0, to the queue and creating an empty visited set. In the first BFS iteration, we dequeue node 0, check if it matches the destination, 3, which it does not. We mark node 0 as visited and add its unvisited neighbor, 1, to the queue. In the next iteration, we dequeue node 1, check if it matches the destination, which again it does not. We mark node 1 as visited, but it has no unvisited neighbors to add to the queue. At this point, the queue becomes empty, and we terminate the search since the destination node was not found. Hence, we return false, indicating no path exists. In example 3, we examine the simplest possible scenario, a graph with only one node and no edges. The task is to determine if there's a path from node 0 to itself. First, we construct the graph. Since there are no edges, the graph remains empty. Next, we initialize BFS with the source node, 0, in the queue and an empty visited set. In the first BFS iteration, we dequeue node 0 and check if it matches the destination, which it does since the source and destination are the same. As a result, we return true immediately, indicating that a path exists. This trivial case highlights that a single node is always connected to itself. Through these examples, we've seen how the BFS algorithm systematically explores nodes layer by layer to determine if a path exists between the source and destination in various graph structures. Whether the graph is connected, disconnected, or consists of a single node, BFS ensures every reachable node is explored until the destination is found or all possibilities are exhausted. This approach guarantees a correct result for the problem, demonstrating the versatility of graph traversal techniques in solving connectivity problems. To analyze the time complexity of the valid path algorithm, we break it down into two main steps: constructing the graph and performing the BFS traversal. First, when constructing the graph, we use an adjacency list representation. For each edge, u, v, we add the connection to the adjacency list twice, once for u and once for v. If the graph contains m edges, this step requires O, m, time, as we iterate through each edge and perform constant time operations for each addition. Next, during the BFS traversal, we explore all nodes and their neighbors. In the worst case, BFS visits all n nodes and processes all m edges. Each node is added to the visited set in constant time, and each edge is processed at most twice, once from each endpoint. This results in a traversal cost of O, n plus m. Combining these two steps, the overall time complexity depends on the sum of building the graph and performing BFS, which is O, n plus m. Now that we've calculated the time complexity, let's look at the space complexity of the algorithm. The memory usage primarily comes from three components: the adjacency list, the visited set, and the BFS queue. First, for the adjacency list, each node stores a list of its neighbors, and since each edge contributes two entries, one for each endpoint, the total space required for the adjacency list is O, n plus m. Next, the visited set is used to track which nodes have already been explored. In the worst case, all n nodes could be visited, so the set requires O, n, space. Finally, the BFS queue is used to manage the nodes that are actively being explored. In the worst case, it could store up to n nodes, which also requires O, n, space. Summing these components, the overall space complexity is O, n plus m. Combining all components, the total space complexity of the algorithm is determined to be O, n plus m. Now let's discuss how the algorithm behaves under different scenarios. In the best case, the source and destination nodes are the same. Here, BFS terminates immediately, resulting in a time complexity of O, 1, since no traversal is needed. However, space complexity remains O, n plus m, because the graph must still be constructed. For the average case, BFS traverses part of the graph before reaching the destination. The exact time depends on the graph structure, but the complexity remains bounded by O, n plus m in the worst case. Finally, in the worst case, BFS explores the entire graph. This happens when the graph is fully connected, and the destination is the farthest node from the source. In this scenario, both time and space complexities are O, n plus m, as BFS processes all nodes and edges. Finally, let's compare this BFS-based approach to a brute force method. A brute force algorithm might attempt to enumerate all possible paths between the source and destination. While feasible for small graphs, this becomes computationally infeasible for larger graphs. For example, in a fully connected graph with n nodes, the number of potential paths grows exponentially, leading to a time complexity of O, 2 to the power of n, or worse. In contrast, the BFS-based solution efficiently explores the graph in O, n plus m, time, making it well-suited for both sparse and dense graphs. Mathematically, this efficiency can be proven by observing that graph construction takes O, m, time to iterate over all edges, while BFS requires O, n, for visiting nodes and O, m, for processing edges. The total work is bounded by O, n plus m, making the algorithm optimal for solving this problem within the constraints. When solving this problem, there are several common mistakes to watch out for. First, it's crucial to remember that the graph is undirected. This means that if there's an edge from node U to node V, the reverse edge from V to U must also be considered. Forgetting this can lead to incomplete or incorrect results, especially when building the adjacency list or matrix. Another pitfall is using an adjacency matrix for large graphs. While it might seem straightforward, adjacency matrices are memory intensive, particularly for sparse graphs. For instance, a graph with 100,000 nodes and edges would require too much memory if represented with a matrix, whereas an adjacency list would be far more efficient. Additionally, assuming the graph is fully connected can be problematic. Always account for disconnected components, as nodes and separate components may not have a path between them. Infinite loops are another issue, especially in DFS or BFS implementations. This happens when nodes are not marked as visited, so it's important to maintain a visited set or array to avoid reprocessing them. Lastly, skipping edge cases can lead to bugs. For example, you should test scenarios with a single node, no edges, or unreachable nodes to ensure your solution handles all possibilities correctly. Now, let's shift our focus to insights that can help during interviews. Being proficient in both DFS and BFS is essential for graph problems. While BFS is commonly used for shortest path problems, DFS can be more intuitive for exploring general connectivity. It's also important to understand the trade-offs between graph representations. For sparse graphs, an adjacency list is space-efficient, whereas an adjacency matrix might be better for dense graphs or when you frequently check for edge existence. Highlighting edge cases during an interview can showcase your problem-solving thoroughness. For example, consider disconnected graphs, self-loops, or isolated nodes, and explain how your solution addresses these scenarios. Additionally, be ready to analyze the time and space complexity of your approach. For instance, when using an adjacency list, both DFS and BFS have a time complexity of O, n plus E, where n is the number of nodes and E is the number of edges. Finally, practicing related problems can strengthen your understanding. Problems like LeetCode 200, which explores connected components in a 2D grid, or LeetCode 323, which counts connected components, are excellent for building foundational skills. Similarly, LeetCode 133 and 695 challenge you to handle graph traversal and apply DFS or BFS in different contexts. Exploring alternative approaches and their trade-offs can give you an edge when tackling this type of problem. One powerful method is the union-find algorithm, also known as disjoint set union. This is particularly efficient for checking connectivity when there are multiple path queries, as it operates in nearly constant time per operation using path compression and union by rank. However, keep in mind that union find requires pre-processing the graph, which makes it less suitable for dynamic scenarios where the graph changes frequently. Comparing DFS and BFS, both are viable options, but each has its strengths. BFS is often preferred for its iterative nature, which avoids the risk of stack overflow in deep recursion. It's also better suited for problems where memory constraints matter. On the other hand, DFS can be simpler to implement, especially in recursive form. For large graphs, bidirectional search can be an efficient alternative. By exploring the graph simultaneously from the source and destination nodes, bidirectional BFS reduces the search space significantly. However, it does require additional logic to manage two queues and combine their results effectively. Carefully choosing the right approach based on the problem's constraints can greatly improve your solution's efficiency and clarity. Great job! We've successfully solved the problem and learned valuable graph traversal techniques. Remember, mastering algorithms like DFS and BFS can help you tackle many real-world challenges in graphs. Keep practicing, and feel free to revisit this lesson anytime. Thank you for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!